taking a step between 2 points on the same body, right? And then imposing, so you take a step from one point to another point is what we do, right? The method that we have is we're going to start at one point that we know something about, and we're going to step out to a point that we want to know something about. And you would do that using this equation, right? And then the process goes, we take a step from one point to another point, and then another point to another point, and along the way, you impose all your constraints, right? The constraint that we imposed here was the velocity at A was equal to 0, the velocity at B was equal to 0, and the velocity at P was the same for both bodies, right? So those are our all the constraints. And as we moved along, we applied all those constraints. And at some point, you'll hit an equation, right? Like in this case, we set our two velocities equal to each other, right? You'll hit a point where you have that, two equations, or I guess some equation on one side and equation on the other side. And what we do is we just look in the x and we look in the y, and that's all the equations that we need to solve it, okay? So then, we talked about rolling wheel kinematics. One of the constraints with rolling wheel kinematics is the velocity right here at the bottom is 0. Then we did a couple of example problems. We went from here to here, here to here, here to here, imposing the constraints that all of these velocities are at the same at all these joints. And then this acceleration and this velocity and this velocity are 0. Then we got to a point where we then, had our big equation like this. We looked in the x, then we looked in the y, and we solved for the unknowns. Right? And that's the process that we're going to use for all of these. Same thing here. Took a step from here to here, here to here, imposed a constraint that this thing was stuck on this bar, ended up with an equation like this, right? And then we looked in the x, right? Then we looked in the y, and then we solved for the unknowns, right? Then we moved on and we looked at accelerations, right? Because the same process can be applied for determining accelerations. Why we care about accelerations is because these are tied to forces and moments, right? Forces and moments. And that's what we're after, right? As engineers, we need to know the forces and moments so that we can design these elements, okay? And that's what actually today we'll move into that realm. Right now, so far, everything's kinematics. It's just geometry, right? But after today, we're going to move into relating all of this stuff to forces and moments, right? So here's our equation for taking a step from one point to another point on a rigid body in terms of accelerations, right? AB is equal to AA plus alpha crossed with RB is seen from A. That's our tangential acceleration. And then this omega crossed with RB is seen from A is our centripetal acceleration, right? In vector notation. And it's really nice to leave it in vector notation because it'll take care of all of the different directions and is it rotating one way or the other way. It's going to take care of all that stuff for us. It's all the heavy lifting is going to be done by the math, basically. Right? And then here's the one that we're going to use for planar. This omega crossed with RB is seen from A. It simplifies down to simply this, right? Whereas you just have the omega squared as a scalar out front, and then RB is seen from A as your vector. It tells you which direction it's going, right? Which is nice to not have to carry out the double cross product. When we get to 3D, we have to carry out the double cross product. We applied this to a rolling wheel. Right? The key things here with rolling wheel kinematics is that we get at point C, it has 0 acceleration in the x direction, but it has a centripetal acceleration at the bottom there, but 0 in the tangential direction. And then RA has no centripetal acceleration, point A has no centripetal acceleration, but it does have a tangential acceleration, which I'd buy that, okay? So we apply that. So you're going to have to use those later on in some problems. This next homework, you get to do a thing called a sun gear with velocities and accelerations. And that thing is super fun, right? It's got this gear in the middle and then these planetary gears and then this big thing on the outside and you have to step around in it. Right? I'm sure none of you will get lost in the process. Even like my solution to one of them is like, I write kind of big. But it was about 2 pages long of just stepping from one point, like all the way around. It's the one that has like this arm coming out, and there's this like sun thing going like this, and it moves as it goes across. It's a good time. Get an energy drink, just sit down, just start hammering away, and then you'll make a wrong negative sign like up at the beginning, and then your answer will be off at the very end, and then you'll have to go back and redo all this math along the way. Good times. Good times. Okay, so we're in the process of this guy. right? So this guy, right, you got a slotted here and we got a slot right here. And then we are given the velocity of point A is in the x direction like this, and the acceleration of A is back to the right like that, okay? And so, and then we're asked for alpha, the angular acceleration of this link is what we're asked for, okay? And so you get going, right? This is an acceleration problem. So you're like, oh, I'm gonna do accelerations first, right? That would be not a bad assumption. The problem with doing accelerations first is, is that equation, wherever it's at, this right here. Here's my acceleration equation. I need to know what omega is, right? You can't do it without omega. And so if you did try starting out with accelerations, you would say, oh, shit, I don't know what omega is. So then what do you have to do? You have to go back and do velocities first, right? In our case, I'm smart and a doctor, and so I've done this before, and so I knew that, oh, we should probably do velocities first, right? And that would be a clue. If you're starting to do this problem and you're like, oh, I'm doing accelerations, and sometimes I'll give you omega, or the book will give you omega, and then you don't have to worry about it. It's just the omega going into it. But in this case, we didn't know what it was, so we had to do velocities, right? So we went through, we did that. We figured out what this RB is seen from A is. It's 0.212 in the I plus 0.212 in the J. Right? And then we imposed the velocity of point B is only in the J direction, and the velocity of point A is only in the I direction. So I just kind of put those in from the get-go there, right? So this is the velocity of A plus omega is in the K direction. I cross this with 0.212 in the I and plus 0.212 in the J. Again, I don't know if omega is a positive or a negative, right? I mean, I do, right? I do, right? Because I know if this is moving this way, it's going to be going that way, right? But I just put it in there as being a positive. I just say it's a positive, and then when I go through and I solve for omega, it gives me a negative. So that just tells me that it actually is rotating in the negative direction, which say that as this thing moves to this direction, omega is falling down like that, which it should be. Okay, so now we have omega. So now we can go on to accelerations. So now I'm going to do accelerations, and they tell me what AA is, and I'm going to go from AA to AB. That's what we started doing. AB is equal to AA plus alpha crossed with RB is seen from A minus omega squared RB is seen from A. So I just plugged in my values right there. AB in the J is equal to 16 in the I plus alpha in the K crossed with 0.212 in the I and J minus, and again, I just put in the scalar omega and I square it, right? And then I multiply it by RB is seen from A. The direction of that centripetal acceleration strictly comes from the RB is seen from A. And it makes sense, right? The centripetal acceleration will be back towards the middle, right? It'll be in this direction, right? And so that's why you just put the scalar out front. All right, so let's just keep going with this one. That was a big review. It's been since last Wednesday since we've looked at this problem, so. Okay. I mean, this is it. I mean, that's it, right? That is 90% of the thinking part, right? The rest of it is just math, right? And if you learn how to do these things on your calculator, right, it really helps with the math, because then you really don't have to worry. No right hand rule stuff as you're going along, right? You just kind of just plug everything in there and crank them out. Okay. So in fact, I didn't even do this part. Although that would be good exercise for you, ... And we'll just say, carry out cross products and combine I's and J's and look in X and Y. Look in X and Y directions. And when you do it, I mean, when I say that it's just like, oh, figure out how to do it, I mean, really document what it is that you did, right? And just be, if you're going to do it by hand and just one element at a time, again, just be really careful. Just be really super tedious as you go through all those steps, right? And just really double check. The biggest problem is like a positive versus a negative in different locations, right? So just be really careful of that. It'll make your life a lot easier if you catch those mistakes up front. Oh, or don't make mistakes, I should say. X direction. 0 is equal to 16 minus 0.212 alpha minus 10.59. And the y direction, I don't know. So y's, let's call it y's. You get AB is equal to 0.2212 alpha minus 10.59. Two equations, two unknowns. Two equations, two unknowns. So then you get out of this alpha is equal to 25.5 rads per second squared. And then AB is equal to negative 5.2 meters per second squared. Okay. Like I said, I skipped a lot of the math along the way, but that's it, right? These aren't super complicated problems. It's just the tediousness. Right? If you set it up all right and you make a little mistake in your cross products, that's going to be a small deduction. In this world, in academia, that's a small deduction. If you design a part or something like that and you made a mistake like this, that's a big deduction, right? That's a big deduction if somebody actually made this. But in this class, we're still in the protected world of academia. Just setting it up is the big one. Okay. I guess the thing to point out here is this is where I think I don't think you can just look at this thing and be like, oh, I'm gonna freehand this thing, because you could kind of do it. Like you could look at this and be like, okay, yeah, I mean, if this thing has a velocity this way, then I know that it's going to have an omega that way. And you could kind of deduce what like the omega would be based off of, just like when some of you guys solved the airplane problem where you just applied logic and you're like, oh, I'm going to keep drawing these lines and I'm going to see where it is that they have to cross. And then I'm going to go through and I'm going to back calculate. Oh, a bunch of people solved it that way. That's great. Right, but you're applying your intuition. You're like, I could do. Here, I don't think. Once you start moving to this world, don't do that. Just stick to this process. It's going to help you a lot, right? Because, like I said, you just, right. I mean, just right off the get go, this thing has an acceleration to the right of 16 meters per second squared. Right, that's what it ends up being. And so I would say my intuition would say this thing should be accelerating up. Right? If this is accelerating to the right, this should be accelerating up. But did you see what we got? We got this thing accelerating down, right? What the hell? Well, how is that happening? Right? How is it doing that? Well, it's because of that centripetal acceleration. We have a centripetal acceleration that's going down and to the left that's overpowering the fact that this thing has an acceleration to the right. It's actually accelerating up like that, which is just, you don't think that you would look at that and be like, oh, clearly that's what's going to happen. But here though, right, the math tells us it takes it into consideration. Because of that centripetal acceleration, it actually is accelerating up, right? Accelerated down. It's accelerated down, sorry. Right? So just trust this stuff, okay? Just be careful. Be careful of just trying to freehand it. Go free willy. Don't do that, okay? All right, so this is I just want to show you, right? I have no trouble with you guys whatsoever, because, I mean, keep in mind, right? You're going to see some of these problems take a very long time to work yourself all the way around, or like that sun gear that you're going to have, right? The planetary gears. It's going to take a long time and like several pages worth of stuff and throwing stuff up. I cannot ask a problem like that on an exam, right? You only have 25 minutes per problem. I can't go that deep, right? I got to do something like this. This is a little bit more straightforward, right? So I have no trouble when you're doing this, but you also have to get exercises trying some of the harder problems. I have no problem with you whatsoever using MATLAB to help with this. Every once in a while, there are 2 or 3 of you because you've learned MATLAB, correct? Technically, you've been exposed to MATLAB in some capacity. You're like, when would I ever use this? MATLAB and I are buddies, okay? We spent a lot of time together, right? And my whole dissertation was coding stuff up in MATLAB, and I love it. I love MATLAB, and I'm pretty darn good with it, okay? But anyways, here's an application that you can apply to your actual engineering field, right? And some of these big sun gears and stuff, go for it. go for it. I mean, MATLAB, it stands for Matrix Laboratory, right? All these vectors are really actually just matrices, right? They're just flat matrices, right? But this is the same problem up above that I just kind of worked out in MATLAB, just so you can see it if you want to refresh yourself on how MATLAB works, right? But so this is done. I think these are symbolic. Or sorry, I had to do some symbolic toolboxes and stuff like that along the way because it's by default MATLAB wants numbers and everything. So this is the problem above, right? That's this problem. So I started out, I defined what VA was, right? Negative 1.5 in the X, and then I defined what AA is. Those are given to us, right? And then again, I'm putting them in vector form like this. This is the I, J, and K direction, right? Then I defined what RB is seen from A is. Right? There's that 0.212 in the I, 0.212 in the J, right? Then I set up what omega was. It's just, that's an unknown, so I had to put it in there as a symbol. So I said that 0, 0, and omega in the K direction. That's where I assume that it's a positive omega in the K direction, right? And then I say, what is VB, the velocity of B, is equal to VA plus the cross product of omega V crossed with RB as seen from A. There it is, right, in its symbolic form, right? With there you see the omegas floating around. Then I say what VB at 2 is, right? There's where I add the constraint that it's only in the J direction, right? And then I solved. I said, yep, VB of V is equal to VB2, right? And then that's where I get this, what VB is and where my omega is. There's my omega of 0.707, or negative 0.707. That's what this omega is. So I used the solve thing. Then I went through and I just kept going with it. And I found my accelerations, my acceleration of A plus the cross of these things minus omega squared, right? Let it take care of that. Then I just set up this. I did again, I solved, I set in the left-hand side equal to the right-hand side, and that's what I get. And I said, tell me what those numbers actually are. That's what the last steps are. The eval is like, tell me what the actual numbers are. And there they are. That's what we just found, right? Is that easier? In this level of this first problem, probably not. Maybe. I mean, doing this by hand, you got the cross here, the cross there, losing track of stuff, maybe, right? I think the calculator, doing this on your calculator would be really slick, where you set up the vectors and stuff in there in your calculator would be nice. But I just wanted to show you that. I'll do that a couple other times throughout, because especially when you're doing those big sun gears and stuff, then things get out of hand. But I gave you that. If you want to try it, go for it. Okay. Let's look at this. Okay, let's do this one. So this one, the angular velocity acceleration of bar AB are omega AB equal to 2 radians per second. So they tell us what this omega is down here, right? They do not tell us what the omega of this bar is. Determine the angular velocity and angular acceleration of bar BD between here and here. Right, so they were after this omega and this alpha. Okay, so in this case, right, since they didn't tell us, right, like, okay, for accelerations, right, I would go from here to here and then here to here, and then I'd apply a constraint that this thing is stuck in that direction. But, right, I need to know, in order to do that jump, I need to know what this omega is. Since we're in this one, I'm going to skip the velocities, but you would have to start out with velocities. Just going to but technically, you're right, you should notice that, oh, yep, I absolutely need those omegas. The omega that I need is of this guy, right? To go from here to here, I need to know what this omega is, right? But I'll tell you what that is right now. But the way you would do it is you do velocities. I go from here to here, then I go here to here. I could put this a constraint that's stuck in the X direction. And then when I did that, right, I would look in the X and look in the Y, and it would show me that I would tell me what this omega is, okay? And that's what I did earlier. And this becomes, or I guess this is omega BD, ends up being equal to negative 2.67. That's per second. For the sake of time, I'm not going to do it. Boop. Okay, so now let's come down for accelerations. All right, we go AB. And I'm going to start out with AA, right? Because I know that that velocity is 0. AA plus omega AB vector cross, oh, no, I wasn't done yet. Alpha AB crossed with R B C from A minus omega AB squared times R B seen from A. And this one you gotta be careful of your subscripts because there's a couple omegas and a couple alphas floating around. A is 0. Alpha AB, they give it to us, right? Alpha AB is 6 radians per second squared, positive 6 radians per second squared. So this is 6 in the K. I crossed it with RB is seen from A. RB is seen from A. Again, these directions are important. I'm at A, I'm going to B. That one right there. So that's 0.312 in the I. 0.312 in the I. I don't know why I put it in parentheses, but I did. Minus omega AB was given to us. Omega AB is 2 radians per second. Oh, I wasn't done yet. There's no 1 in there. Beep. I was just going to say, what's wrong with this? Hey, so I got it from here. This 0.32. That was a nice way to put it. Where did you get it? Like, I was right, right? You must have been. That was a good way to put it. Who said that? Yeah, Mark, that's good. That's good. You made me feel better. It's like, where'd you get that? I just curious. I'm not going to point out that you made a mistake, dumbass, right? But you must be right, Mike, because you wrote that. Of course you wouldn't have done that. Yeah, good. Negative AB is a positive 2. So 2 squared times 0.31. 312, I did it again. 32, I don't know why I want a 1 in there. I've got parentheses all over the place too, but. Okay. 6 in the K, cross with 0.312. Oh, fuck. 0.32 in the I minus omega squared, with 2 was given to us, times 0.32 in the I direction is that direction. So if you carry that out, this just ends up being equal to negative 1.28 in the I direction plus 1.92 in the J direction. Okay. So this one's saying that I'm going to have an acceleration back towards the middle of 1.28 in the I, and then I'm also going to have an acceleration up of 1.92 in the J. Right. So the tangential acceleration, that guy, comes with that, or that's the tangential. That's the R alpha term, and then this one right here is the R omega term. And again, that passes the stink test. I would absolutely believe in those. So again, I said before, trust this math, but then also go back and just see if you could convince yourself intuitively if that would make sense. Right? In this case, it would make sense, right? That is, it should be accelerating back this way and up, which it does. Okay, and we go on. We know that, so now I can take a step from here to here, right? Could I go from here to here? Absolutely. I could go to point D, but I can't, I could do it, but then the problem would be, D isn't constrained at all. So if I took B to D, I would just end up with some equations. Sure, if I asked what is the velocity and acceleration at D, I could absolutely take a step from B to D, but that doesn't help us at all. I need to go to someplace where there's a constraint. The constraint in this case is this bar right here, right? So I'm going to take a step to C instead, right? And then I'm going to apply the constraint that C can only accelerate back and forth in the I direction. Right? So that's what I do. I go AC is equal to AB plus alpha BD crossed with RC is seen from B minus omega BD squared times RC is seen from B. Okay. This is where if I hadn't done velocity to begin with, then I would be bogged down because I need to know what omega BD is. Okay. All right. AC, just plug in everything I got, equal to AB, which is negative 1.28 in the I, plus 1.92 in the J, plus alpha BD in the K. I don't know if it's positive or negative, but I just put it in as a positive, always in the K direction. I cross that with, now I need this. RC is seen from B. I'm going to go over 0.24 in the I, and then up 0.48 in the J. All right? This would be 0.24 in the I plus 0.48 in the J minus a negative 2.67 squared. That's what I had from before. I gave you that before. Times 0.24 in the I plus 0.48 in the J. Okay. You're getting a feel for the tediousness of these problems, right? Once you lay it out. I mean, that's the hard part right there. It's not even that hard. Uh-oh. Right. So at this point, right, you carry out these cross products, carry out this cross product. Actually, that's the only cross product you got is that, right? And then carry out the math associated with this. Lump all your I's, lump all your J's, look in your X, look in your Y, right? I'm gonna punt again. I'm gonna say ... right? In fact, all you need to answer this, it's only after alpha, so you only have to look in the Y direction. Technically, I always just look in both directions just in case, but in this one, you only have to look in the Y direction. It's the only ones I wrote down. 0 is equal to 1.92 plus 0.24 alpha BD minus 3.42. They only asked us for alpha, so I just wrote down that part. This you get alpha BD is equal to 6.24 rads per second squared. Okay. Like I said, these appear to be scary at first, but they're not. They're not bad. Tedious, if you will. Okay. So then that's our alpha BD. Now, at this point, if I said, hey, what is the velocity and acceleration at point D, you could do it, right? I could take the, I didn't, let me just skip a part here. I wanted to click, I applied the constraint, but I didn't write it down. The constraint was this AC. You say that it's only in the I direction, so you say it's AC in the I direction plus 0 in the J direction. That's the constraint. I should have included that. right? And so then when you're looking in the J direction, this 0 right here came from that 0 in the J. Okay. So your guys' notes stop there on this section? Do they? The skeleton notes?
Yeah.
They do. Okay, good. Good. We used to do, back in the day, we used to do this type of problem. It's called slotted connections, right? Where one can move relative to the other. And that was a pain in the ass. So I skip it. I skip it now, right? And all it does, it's the same process. You know, you're taking a step from here to here. Those 2 points are on the same body. And I take a step from here to here. Those points aren't on the same body, but they're related in some capacity. One of the reasons I like to skip it is that's what our acceleration equation ends up being, right? When you pick up so this is, you got to step from one point to another point. You know, you end up with this, an extra term there. I pick up, this is what we had before. This is centripetal acceleration, and then this is another one, right? So if this is the tangential acceleration, this is the centripetal acceleration. What do you think this one is? There's only one other kind. It involves toilet bowls. Coriolis, right? So this is your Coriolis. You end up with a Coriolis acceleration when you let things move relative to each other. And like I said, I don't think a lot was gained by doing that. Like the FE exam doesn't have slotted connections. They end up being, even more tedious than these ones just because they blow up on us. So anyways, I cut that out, and I used to accidentally leave it in the skeletons, but good to me, I actually remember taking them out of skeletons. Okay, so the next topic, let me see if I can do something real quick. I just want to show you where you're going in your homework. Hold on. There you go with this. I'm going to show you some homework problems. I'm going to show you the sun gear. I'll be there in a second. So then, just a side note too, right? Like I just extracted my notes from the book. I'm giving you the chapters of the book, right? Read that stuff. Read that stuff. You get to do this one for velocities and accelerations, right? So this is a planetary sun gear. Now, I guess what is the overall? I would call it a sun gear, but what does it say? It says it's a ring gear. They call it a ring gear. I'll have some videos on YouTube Friday this week. I'll show you what this gets used for. It's actually how your automatic transmission works in your car. Is something similar to this, but in this case, right? It looks scary. It kind of is. It kind of is, right? But the whole I can't write on the screen on this one, but what you end up doing is you start out in the middle, right? The velocity, right? One of the things to do is label all your points. So this one doesn't have any points labeled. I would go through and label point A, B, C, D, and stuff like that as you go along. So in this particular problem, this outside ring right here is fixed. And the inside, I think they give you omega of that bar that's sticking up, and then they ask you for what's happening to this gear in the middle here. And so you take a step from the middle out to what I labeled as being point B up at the top, and then I want to draw on this. Hold on, give me a second. Just to kind of get you started, give you some hints. happened to my... You don't want to go there. Right? So I go through, right, and I'd label this, as point A, and then I'm going to call that B. I'm going to call this point C, and then, I guess the key to this one is I think this gear and this gear are stuck together. So whatever this guy rotates, this outer guy rotates. It says something in the problem statement. But what we do is just don't panic. Just stick to this. Our process works for this. So you take a step from here, and then label all the other points, because then you're going to have to come back from down to here too. You're going to have to label this. This will probably maybe be D down here, right? And so then what we do is we go from here, you go up to there, right? Because you can only take a step on the same body, right? And then I know that out here is fixed, right? So I know the velocity of point C is 0. So then I could take a step from here to here. And by relating those two, I could figure out what the omega of this guy is. And once I get the omega of that guy, I could take a step from here down to here. And then I know that the velocity from this point is the same as the velocity of that point coming from the center of this disk, right? And so you just stick to it. I mean, you could see how this takes a while, right? And it's very tedious. You go here to here, here to here, apply the constraint that velocity is 0, then I could take a step from here down to here, and then from here down to here, and then it would tell me what this omega is, right? And at some point they're asking what's happening at the velocity A, but once I determine the omega of this and this together, then I take a step from here up to here. So it's all just about taking steps around this thing. But then what gets difficult is you're going to mess up the math as you go along, right? You're going to mess it up. And then I think you do that one for velocities and you do that one for accelerations. And so these things take a couple of pages of work. And so doing that in MATLAB or at the very least learning how to do these vectors with your calculator would be nice, right? And I think that one isn't the hard one. I think the hard one actually is this guy. That one ends up being a pain in the butt. Right? But then again, just that process is I'd start at E, and then I'd go to D, and then I'd go from D over to B, and then I'd go from B down to the point where those two touch. It's going to be 0 because that thing down at the bottom is 0, and I apply that constraint, and then it'll tell me omega of that one, and then once I get the omega of the big one, then I can figure out what the omega of the other one is. Actually, in this case, sorry, this one they give us they give us this to begin with, and you work this. You start out this way and go that way. And then one of these has the wrong answer in the back of the book. I think this one has the wrong answer in the back of the book, and I'll give you the right answer in my when I post the solutions on this. Right? And you might say again, what are these for? Like, why would I ever want to know this? Well, this one up here, that one, that planetary gear, this one right here is actually somewhat how your automatic transmission works in your car. Any questions about this stuff? This is the kinematics, okay? That's the end of kinematics. The next step is kinetics. All right, so let's go to kinetics. Fall 2020, no, we got this one. Look at this, right? We're on 2D rigid body kinetics. That's 4 of 5 sets of notes, right? I still feel like we just met. That you're just still youngins, just start. Now you're getting it, right? You may have heard of this class before and how it's a weed out class, how scary it was. Hopefully it's not. It's a little scary. Hopefully it's a little scary. But you're also doing it, right? Like we're halfway through. All right, one last little loose end. The book has a big discussion about inertial reference frames. Right, I'm just going to add a couple. I'm just going to summarize. This is like one last little topic. Right? Inertial reference frames. This means reference frame that is not moving. So when they talk about inertial reference frames, if you ever see that, that's what they're meaning. It's just we're taking that to be zero, right? Newton's laws apply to inertial frames, right? And then they have a big discussion with numbers behind it. Is it okay to consider the Earth's surface to be an inertial frame? Yes, for the problems in this class. No, for continental, I don't know how to spell intercontinental, intercontinental ballistics, weather, launching rockets, etc. Right? Just depends. Right? But for the type of problems we're in here, and they have a big, like I said, they back it up with numbers and stuff like that. And there's a whole section on it, but that's what we're gonna say, right? And that's okay. We've discussed that before. It's always, it's always, I don't know what's going on. It's just a weird topic, right? Because again, right, if you really wanted to be really careful and pick something that's not moving, right? Well, again, it gets difficult because it's not the Earth's surface, because that's rotating around. It's not the center of the Earth, because that's rotating around the sun. It's not the sun, because the sun's rotating around the center of the Milky Way, right? What is it, right? And in fact, there's no way to prove that what is moving and what is not moving. Maybe we are. Maybe it's revolving around me. Maybe I'm the one thing that's not moving, and everything else in the world is moving, and the universe is moving relative to me, and I'm the 0 point, right? It's impossible to tell ever what's moving and not moving. So, but we're in this class going to assume that it's the center of the Earth. One thing, something that keeps me up at night sometimes is you think about like the vastness of the universe going out, right? Because it's infinite, right? It just keeps going out. It's just vast. It just goes on forever. It's hard to conceive. But what blows my mind, that freaks me out, is the same is true going down, going smaller. It can go smaller and smaller infinitely forever and ever, right? And we keep learning about, the atoms. By the way, we've never seen an atom, but we know they exist, and we can even blow them up, right? We can even split them, and like it's so. And then we make the chemistry. I read a book about. I don't read, but I listened to a book, an audio book, and it was like I'll have to look it up. It was like the science of everything, and it literally started just in the 20s, right? In the 20s, they were like, you know what? I think there's these little particles that everything's made up of, right? And then I think Einstein, you could look at little things, you could see little vibrations, and they have these little clues of what was happening. And then somebody's like, oh, guess what? I think all of them, we can actually put it into this like periodic table that there's like these things called electrons and there's nuclei and protons and stuff. They've never seen these things. So they just start guessing. Oh, I think that's what it is. And then I think that's what it is. And then, oh, guess what? Like, look at this. And then they started like how they discovered it back in the day with the technology that they had, right? And then all these people, it's nuts. And all these people are dying from radiation because they're exposing themselves to these, you should consider having that book read to you in your ears while you walk, right? Because it is really cool. It is really cool I hadn't even thought of that before, like with the technology back in the day, how they discovered these things. Like, and then again in the 40s, they were able to determine that, oh, by the way, we could start off this reaction that will if you don't know how the atomic bomb works, right, is there's like, it releases these little electrons go out and they hit the proton, or they hit the nuclei of an unstable thing, which splits, and then the next one goes and right, and it becomes unstable each time. And so what it ends up being is it's a chain reaction of all of these. It makes it sound like when you get told it's like, oh, we split the atoms, and then all this energy release. That's not what happens, right? Is you have this unstable element, and then you have this big glob of it, this really big glob of unstable element, this has nothing to do with dynamics. But then, and then this little, they impose. There's two different ways they did it. They had the fat man and little boy, fat man and little boy, and they both had different ways that they did this, right? And one of them was they squished it more until they had these explosions that went off around it that squished it more, so then it pushed it into the unstable range, and then it started the chain reaction. And then the other one, they had a little plunger that went into the middle of it, and then that caused the unstable reactions. They had two different ones, and they both, by the way, they both worked. Right? Like they tried it out, and the first time they tried it, it worked. Right? Unbelievable. Right? And then it was like literally like 2 weeks later, they shipped it to Japan and did that. Right? I mean, you guys all seen the movie, right? Like, I read a book about that too. That is nuts. I didn't read it, had it read to me, right? But anyways, the fact that they were able to figure that stuff out is just, but infinitely small. That was my point. Is you could keep going, because first they were like, oh, we got these things, they're atoms. But then inside the atoms, now they start dealing with quarks, right? And they've named them. Isn't that weird? Like a top, or an up, a down, top, bottom, right? It's immediately. Do you guys learn that in high school, or where did you learn that stuff? Nowhere. Okay, because I didn't ever learn it. I just read about it. It was a crossword puzzle. They're like, 2 ups and a down equal what? And I was like, fuck if I know. And it was a proton. It's made up. But see, they determined that those things exist. But then what are those made of? Right? What are the quarks made of? Right? Well, they're made of, pure energy or something. But then what is that made of? And what is that made of? And what is that made of? The fact that the universe just keeps going smaller and smaller. Okay. Anyways, we'll start this next time. Right. Science is cool. If you believe in that sort of thing. Right? If you believe in that sort of thing.
Excuse me, which calculator model do you have?
I have